Thanks for being here. We are having a conversations with Dr. Bill Daly, Chief Scientist and Senior Vice President of Research at NVIDIA. Bill has been the chairman of the computer science at Stanford University before, where trained and mentored many of the big thinkers and brains in the AI field today, and you're all in a thread of conversations with Bill about where we came, how AI field came to what it is today, and get his brain on where it's going. So Bill, thanks so very much for being here. Really looking forward to the conversation. Let's start by kind of looking at the history, and if you had to identify the single most important breakthrough that enabled AI capabilities today, what would that be?
I think without a doubt it's GPU computing, because that was really the thing that was missing. The algorithms had been around since the 1980s. Large label data sets have been around for a decade, but it wasn't until we had GPUs with enough computing power to train a large enough model on a large enough data set in a reasonable amount of time that sort of ignited the air-fuel mixture of the data and algorithms to really create the AI revolution we have today. So without, the hardware was the enabling thing. The other pieces were there already.
So I don't know if the story is true or not, but something that I heard or read is that the sort of getting to know GPU was that a graduate student at Stanford in his dormitory was doing his homework and started using his gaming computer to do their machine learning algorithm homework, and they all saw the efficiency, and that's where it took off. I think it's a cute story. Let me ask you the other side of that question, that what fundamental assumptions about AI that were widely held 5 or 6, 7 years ago that you think that they are not valid today?
I don't think there's anything that people thought 5 or 6 years ago, we're talking about 2018, that really aren't still valid today. I think the one slight misunderstanding people had is, back then I think many people thought that just by scaling the size of models that we would continue to increase performance. And I think the realization people came to is that data is more important than scaling the size of models, or probably more accurately that the two need to be scaled simultaneously. You need both more data and better data. You have to curate it very carefully to continue to improve the accuracy of models. I think the period of time when there were some really big misunderstandings in AI goes back to the 80s and 90s, when many people dismissed neural networks as being toys. And I think they were simply wrong. I think neural networks were then and remain a very powerful technology. And at the time, in the 80s and 90s, the compute that was available was simply not powerful enough to do anything useful with them. But the neural networks were really a great technology, and I think many people dismissed them and set the field back quite a bit by doing that.
I remember I trained a neural net. This is back in 2003 as part of my job at NIST, and then the committee that review our work came and asked me that, why did you pick neural net? Nobody's using that today. And I just said, well, that was the one that worked. Staying on the topic of the scaling that you mentioned, what breakthroughs would be needed to achieve human-level performance, whatever that means, in areas that AI still significantly lack? You just kind of respond that, but I asked the question, do you think scaling is going to take us there? And how do you see the balance of pursuing incremental scaling improvement versus investing in potentially paradigm-shifting research and what those directions could be?
Yeah, I don't think we're going to get to human-level performance in areas that have resisted it simply by scaling. I think it's going to require new perspectives and new inventions, new technologies, new approaches to get there. I think it's going to require a lot of effort and a lot of creativity, a lot of experimentation, and many things that we try won't work before we hit on the ones that do. I think it's a long road ahead.
So which research direction do you see or do you foresee that's going to take us there?
I think, just to look at some things in the recent past that have improved capability, one is chain of thought and tree of thought, where rather than running a model a single time, we'll run a model and then we'll take the output of that and run it into the model again, often with different branches. We'll actually try different outputs and then prune off the ones that aren't working and pursue it. That's taken a model and boosted it, a relatively simple model, and boosted its performance over that of more complex models. The other thing that's been very effective recently is agentic systems where we give models tools. If your job is to do a mathematical calculation, you're much better off taking a simple model and allowing it to use a calculator than taking absolutely the most state-of-the-art model and trying to make it you do the math calculations just with a large language model. So combining multiple models together in an agentic system is a very powerful composition. I think tools like that, where you take the model as a building block and you combine it with other tools and with multiple passes through the model, is the direction that's going to wind up getting better performance.
I have a lot of questions on agentic AI, but I'm going to move on other topics, and if we had time, I'll get back to that. What would it take to make training large models 100 times more efficient? Is that a realistic goal? And do you think we need more hardware and advances or more of the software and algorithmic breakthrough? Yeah. Where is the major driver?
Well, I think we're going to need both hardware and software to get another 100x. To put things in perspective, over the last decade, we've improved the energy efficiency of training large models by 1,000x on NVIDIA GPUs, and only 2.5x of that 1,000x has come from semiconductor process technology. The other 400x has come from better hardware design. And I think that there's still a number of things we can do in hardware design that will improve things, and I think at the same time, we're going to get better algorithmic improvements. We're going to be able to get more performance out of simpler models, basically using the bits more efficiently. So the combination of the two together, I think, will get us there.
And just with a finer point on that, you're talking about new, better design of the chips of tomorrow rather than manufacturing of them.
Yeah, I don't think we're going to get any substantive improvements from better chip manufacturing technology. We really haven't seen much improvement. I mean, we get more devices on the chip, but their energy efficiency has improved only very slightly. That's why going from 28 nanometers in the Kepler generation to 4 nanometers in the Blackwell generation has been a 2.5x from the technology. The other has been all from design improvements. So I think going forward, if we're going to get another 100x and say 10x of that's going to come from hardware, 10x from software, that 10x from hardware is going to be almost entirely from better design, not from better semiconductor process.
Wow. Those are still very impressive goals. I'm going to switch the topic and ask a question about sort of the direction of the technology. Many transformative technologies also had unintended consequences, those that cannot be foreseen or tested carefully by their creators. So how do you see the AI researchers and technologies should balance pushing the boundaries of the science, of the technology and innovations through what is possible and taking it beyond, but also considering potential negative consequences?
So I think as developers of AI, we need to be cognizant of potential misuse of the technology and make sure that we put adequate guardrails in place to the extent possible to limit bad things that can be done with technology. But I don't think that should impede or slow us in trying to build the best models we can and deliver the best performance for positive uses of the technology.
So those guardrails can be part of the better design of the systems, can be sort of a guardrails after the system is designed as part of the deployment. How do you see there, and how do you see areas for research as part of building models and chips that are secure by design, privacy enhanced by design, and all of those?
No, we actually have an active research area trying to improve security of AI models. At the same time, you need many different mitigations. So you want to, as you train the model, align the model so it cannot respond in certain ways that are known to be negative. At the same time, you typically want to then put a scaffolding around the model that will also try to both find prompts to the model and outputs of the model that should be suppressed because they're negative or treading into territory that the model shouldn't be dealing with. And then finally, one of the biggest misuses of AI these days is in creating fake media of many types. And the real mitigation there is taking advantage of provenance and authentication technology to basically cryptographically sign media that's been authentically created. For example, if everybody's iPhone signed every image and every video that it took, and then that cryptographic authentication was propagated through the system, people would be able to know when an image or a video is authentic, and be skeptical of anything that's not so authenticated.
Authenticating the authenticity rather than trying to chase the deepfake. That's something that we have been talking for a long time.
Yeah, I think it's easier to, stamp the known content, the known good content as known good, than it is to try to, chase identifying the fake content, because that's kind of one of these arms races where as soon as you get good at spotting one artifact, the people who are generating the fakes will, modify their models to not generate that artifact, and you constantly have to, improve.
Plus that you have a more cooperative users to authenticate the right content. What you said made me think and asking you that, so we're talking about AI being misused, and a lot of people are also talking about misaligned AI. So in the first scenario, it's people that we have to worry about that getting something bad. In second scenario, it's AI that we have to worry about. Where do you see the spectrum? Which part you worry more about this?
Well, I mean, AI often gets the answer wrong, but I'll distinguish wrong from bad. So AI will give us wrong answers occasionally. It will hallucinate and not, give correct information. But I think misuse requires, sort of a person with malintent to take the AI, even if it's giving the right answer, and apply it to a negative purpose.
So which one you worry more?
I worry more about people.
The whole part. So moving to a different topic, AI has been progressing from perception AI to generative AI to now physical AI with all of the humanoid robots where code intelligence meets action. What fundamental technical challenges emerge from this new frontier, and how do the requirements for AI system change when they need to operate reliably in a physical environment rather than just relatively digital ones?
Yeah, well, the big gap with going to embodied AI, what we're using in our robotics lab, for example, is lack of data. So what's made progress on large language models so phenomenally quick is the fact that you had this huge corpus of text data on the web that could be mined. So you had terabytes of data that you could feed the model to train it, and you could make it self-labeling by simply taking out every third word or so and training the model to fill in the missing words with with known correct answers. The problem is that doesn't exist for robots. For a robot, you're training a vision language action model, and you need examples that include vision and language and action together, telling the robot to pick up a bottle and fill a wine glass, and then you can have the text that's there, but you don't have the vision or the action of that. And so we're in our laboratories trying to close this gap by generating that data, but it's an expensive and time-consuming process. We tend to do teleoperation experiments. So we'll have a robot, and we'll have a teleoperator, usually with just some gloves that get sensed, gesture, and have the robot follow their gestures, pick up the wine bottle, pour the glass, and then put it down. But somebody just spent 20 minutes, and now you have one piece of training data where you need trillions of such pieces of training data. We have developed some technology that multiplies that data up, so we can do one teleop experiment and then take that digitized experiment, put it in the simulated world, and do variations of it. Move the location of the wine bottle, move the wine glass, fill the glass halfway versus completely full, and get many hundreds of training samples out of one teleop experiment. But it's still a long way to go to get to the amount of data that we need to build really good physical AI models.
Seems like an idea for some startups to kind of generate the data for training robots. I'm going to, having more time, I'm going to pivot to some conversations around the kind of global AI, and how do you see the competition? The competition can be competition on build better design, innovations, can be competition on diffusion, getting the models, everything in use. It can also, we hear about this race to AI, to GAI, so paint a picture for us. How do you see the space?
Yeah, so NVIDIA is an infrastructure company, so we primarily see the competition as competing to provide the world's infrastructure for AI. And I think that's actually a big competition that's going on right now. We have a head start, but there's a lot of competition for that. So we're building our GPUs. There's 100 startup companies building different chips aimed at either training or inference. Some of these are inside of data center companies, like Google makes their TPU. Amazon has their both Trainium and Inferium chips for doing training and inference. I think that's a very healthy competition that will cause everybody to work hard and improve the efficiency, because if they don't, somebody else will, and they'll wind up taking the market. There's also an international side to that competition, where because of export controls, we can't sell GPUs, even H20s, to China, and that's given a wide open playing field for Huawei to sell their parts. And in particular, what it's done, half of the AI researchers in the world are in China, even though it represents only 20% of the AI market for hardware. Up until a few years ago, all of those Chinese researchers were writing software for NVIDIA parts, and that was making the NVIDIA parts more useful, and more importantly, the Huawei parts weren't really useful at all, because none of the software you needed to make them useful was there, and there was no motivation to write that software. Since we've been unable to sell our parts into China, all of those Chinese researchers are now writing software for the Huawei parts. The Huawei parts have become very useful because of that software, and now they're actually a very credible solution. They're less power efficient than our parts, they're inferior in a number of ways, but they get the job done, and because they have this open playing field eliminated from competition, their software is improving much more rapidly than it would have if they'd been competing in a level playing field, and a lot of those programmers would be writing software for other people's parts. So that's one type of competition. I think there's also competition for building models, and I think whoever controls the best models can sort of demand a premium for their API for access to those models. And good models come from all over the world. I mean, especially in the open source arena, Meta is putting out their Llama models, which are quite good. The Mistral models are coming out of France. And I know many AI researchers who use DeepSeek or Qwen, which are open source models coming out of China. So I think that's sort of another arena for competition. But perhaps the most important arena for competition is in applications. I think whoever provides the infrastructure, somebody then provides some models on top of that. That's then used to build an end-to-end application for education, for science, for business processes, and that's where the real value from AI ultimately is created.
And how the US is doing on those type of applications, and where do you see the most important applications that we should focus on that we are not doing it right now?
Yeah, well, I think the US is doing quite well in the applications, but again, everybody in the world is working on this, and it's an international, both competition and cooperation, co-opetition in a way. The areas that I think are somewhat neglected, being a former educator, one is education. I think there's such a huge potential to apply large language models to build AI tutors to help every student realize his or her potential, and also to train the workforce that we're going to need in the future as AI enables a different workforce, a different economy. And AI has this potential of understanding the student, how they learn, what things they're excited about, and then couching the material in a way that is both interesting to them and tailored to the way they learn. I think it could really improve outcomes across the board for education. Another big area where I think we're underinvesting is AI for science. I think there's there's been some very high-profile successes like AlphaFold, which got several people the Nobel Prize in chemistry and such things. But I think there's many other applications where AI can just really advance the pace of science, both by doing simulations using AI rather than traditional numerical methods, but also by having AI agents that act as scientist assistants that have digested all the literature, can suggest which paper you should go look at if you have a question about something, and perhaps even suggest novel hypotheses and experiments to run.
So all that you're saying and talking about is fantastic and can bring a lot of productivity, but also means that the landscape of workforce is going to change. So AI is going to have a huge impact on the labor market. So very quickly tell us about how you use AI in NVIDIA, and then what's the outlook, class of 2026 when they graduate, should they worry about?
So we use AI pretty broadly in NVIDIA. Some of the most common ways is our software engineers use Cursor to help them write code, and what we've found is that improves the performance of the average software engineer by a factor of between 2 and 3 in productivity. So what used to take 2 or 3 people to do, we can now do with 1. And actually, the very good software engineers, it improves their productivity more like 10x. So it's a huge assistant that leverages somebody and lets especially good people get even more things done than they could. We use it in hardware design in a similar way. We have taken a pre-trained model and then fine-tuned it on all of our hardware designs in the past, all of the documentation for them, all of the test code, all of the test results. And now a junior engineer, if he wants to know how the texture unit works, rather than taking up time of a senior engineer, he can ask Chip Nemo, our AI model, and Chip Nemo will explain it to them. That it can generate new hardware units. We tend not to use it for that as much. It's much better at generating tests, which is actually what hardware engineers spend a lot of their time doing, is writing tests. And it's very good at processing bug reports. We'll feed, sometimes a bug report's like 50 pages of here's what went wrong, and it will read those 50 pages and give you a nice 1-paragraph summary and then tell you who should fix the bug, which is the most important part. We call it being ARBed, action required by, in the bug report. And then another really exciting thing we're doing with AI internally is using reinforcement learning for design. When we designed our adders at NVIDIA, they have carry look-ahead circuits in them, which is critical to getting good performance. And we've got a reinforcement learning tool that designs all of those and does better than the best human designs. And it's interesting because typically you want the design to be as inexpensive as possible, the least amount of chip area, the least amount of power, to meet a certain timing goal. And we'll give that constraint to this reinforcement learning tool, and then it starts playing this video game of where to put look-ahead stages in the adder chain. And you'll watch it, you can sort of see the progress as it goes, and it's bizarre, but when it's done, it's completely asymmetrical. It's nothing any human would come up with, but it's really good. That's another great example of
I started
AI
using
for design.
AI to help me with my coding, and I have to say that it feels really liberated, not chasing pointers and looking for the bugs. We are out of time, but it was very quickly, if you have any advice for young talents, people that want to get into figuring out what to study and get to the workforce.
Yeah, well, I guess that was the other half of your other question. So I think anybody who's entering the field should embrace AI and understand how to use it as their partner. And in some sense as their minion, right? Because what it does is it makes all of us more productive and more impactful by being able to automate the kind of routine part of our jobs so we can do the things that are uniquely human and be creative and think big thoughts and have AI kind of fill in the blanks and help us realize our visions.
If we can depend to AI to do the things reliably, because as you said, they still make...
Right, you got to check it.
Yeah, we have to check it, and that's why they...
Yeah, just like a typical assistant, you need to check their work.
Verification, validation, test and evaluations becomes really important. Thank you so very much, everyone. Bill Daly, thank you.